It came from beyond our solar system, a mysterious wanderer streaking through the cosmic dark. It went behind the sun, but now it has reappeared. The interstellar visitor has returned, but it's strangely glowing brighter, pulsing with strange energy after its trip behind the sun. Astronomers are baffled.
Our cosmic visitor, the interstellar wanderer known as 3I/Atlas, has suddenly become the star of a solar system drama nobody could have planned. As it sweeps past the sun, it has sprouted an enormous ion tail, stretching millions of kilometers into space, like a glowing banner in a cosmic parade. And here's the kicker. By sheer astronomical chance, both the Hera spacecraft and Europa Clipper are about to glide right through the comet's extended tail. Two spacecraft, each on entirely unrelated missions, are about to experience a brush with an interstellar object for the very first time. Scientists are practically bouncing in their lab coats at the sheer improbability of it, because opportunities like this don't come around even once in a lifetime. In this video, we'll explore how this unplanned encounter came to be, why researchers are practically doing celebratory cartwheels, and what exciting new discoveries could emerge from these fleeting interactions. 3I/Atlas is only the third confirmed interstellar visitor ever detected in our solar system, joining the likes of Oumuamua and 2I/Borisov in the exclusive club of cosmic wanderers from other stars. It was spotted earlier this year, and as it races toward its closest approach to the sun on October 29th, it has been steadily brightening, a cosmic sunbathing session, if you will, though with far more outgassing than a regular summer tan. The sun's intense radiation heats the comet's surface, causing it to vent gas, dust, and ions into space. These charged particles are then swept back by the solar wind, forming a spectacular tail that streams outward, dancing and shimmering as the solar breeze shapes it. Watching 3I/Atlas approach is like seeing a cosmic flag unfurl in real time, a dynamic, electrified spectacle that astronomers and space enthusiasts alike can't take their eyes off. Meanwhile, humanity's spacecraft are on their own important missions. Blissfully unaware of the tail-chasing party about to unfold, Hera is en route to the asteroid duo Dimorphos and Didymos, tasked with studying how the DART impact altered the smaller asteroid's orbit. It's a mission of careful measurement, cosmic billiards, if you will. Europa Clipper, on the other hand, is heading to Jupiter to investigate the icy moon Europa and assess whether its subsurface ocean could support life. And somehow, without a single meeting planner involved, their paths happen to intersect precisely where 3I/Atlas's tail stretches out, a serendipitous encounter that is astronomically rare. Hera will have a front-row seat from October 25th to November 1st, while Europa Clipper arrives fashionably late, from October 30th through November 6th. Timing has never been so uncanny. It's like the universe has a mischievous sense of scheduling. To predict this improbable alignment, scientists ran orbital simulations and tail predictions through a piece of software affectionately named Tail Catcher. No, that's not a sci-fi gag. It's a real program used to model how charged particles from a comet interact with the solar wind. Tail Catcher predicts the paths of ions, electrons, and dust grains as they are blown away from the comet, giving scientists a map of where these wispy streams of material are likely to drift. According to the software, both spacecraft are expected to pass within roughly 8 million kilometers of the tail's densest stream. That's far enough to avoid a particle hit parade, but close enough that sensitive instruments can sample stray ions and magnetic field variations drifting through the space around the comet. Hera, unfortunately, is attending this cosmic shindig without the right equipment. No plasma detectors, no magnetometers. Basically, it's the guest who forgot the snacks. Still, Hera's precise trajectory data will help ground truth the models and provide a baseline for interpreting any measurements Europa Clipper might capture. Europa Clipper, however, is fully armed for the occasion. It carries instruments designed to probe Europa's magnetic environment, plasma interactions, and radiation environment, all originally intended to study the moon's hidden ocean. These same instruments can, by happy coincidence, detect changes in particle flux and magnetic fields in the comet's tail. If 3I/Atlas's tail nudges the solar wind, Clipper's sensors could catch it in real time. This could reveal how an interstellar comet behaves under the influence of a star it never called home, giving scientists their first close-up view of alien cometary physics. The spacecraft was not built to chase interstellar objects, but in this instance, it's perfectly equipped to observe them, proving that sometimes versatility in spacecraft design pays off in spectacular ways. Of course, the universe rarely delivers a perfectly predictable encounter. The solar wind is capricious, gusting and swirling in ways that can push the comet's tail far from its predicted path. Tailcatcher provides a model, but reality may differ. The tail may twist, wiggle, or stretch in unexpected directions, changing the density and composition of the material through which the spacecraft will fly. This fleeting, unpredictable nature makes the observation both thrilling and challenging. Scientists must be ready for surprises, but even if the tail shifts unexpectedly, any measurement, or even a null result, will improve our understanding of interstellar comet dynamics. For the first time, humanity has a chance to directly measure an object that originated around another star, NWHY. Does this matter so much? Interstellar comets, like 3I/Atlas, are essentially time capsules from other planetary systems. They carry clues about the chemical makeup of planets, comets, and possibly even prebiotic molecules from stars far beyond our own. By measuring their composition, structure, and interaction with the solar wind, we can begin to understand whether our solar system is typical or unusual. Even tiny bits of data could tell us whether 3I/Atlas resembles comets formed around our sun, or whether it carries alien fingerprints that defy our expectations. For the first time, we could have a literal taste of the chemistry of a faraway star system without ever leaving Earth's neighborhood. Scientists have a precise shopping list for what they hope to capture. First, the plasma environment. How many charged particles are floating around? How fast are they moving? And are they calmly drifting or whirling with energy? Next, magnetic fields. How does the comet's tail interact with the solar wind's invisible magnetic strands? Are the field lines twisted, draped, or gently curved? Understanding these interactions is critical for figuring out how comets from other star systems respond to solar forces. Finally, the encounter will allow researchers to test Tailcatcher's predictions, providing the first opportunity to validate such models against an interstellar comet. Success or failure, each data point will help refine our understanding and improve predictions for future cometary encounters. There are, of course, caveats. Both spacecraft will pass through the outer regions of the tail, where particle density is low and signals may be faint. Solar wind gusts could distort the tail unpredictably, making measurements even trickier. And, importantly, these missions were not built for comet chasing. They're adapting on the fly. But science thrives on these kinds of challenges. Even if instruments detect nothing, a null result is still meaningful, helping set constraints and refine models for future observations. And if Europa Clipper does capture data, the results could be revolutionary, the first direct measurements of an interstellar comet in our solar system. It would provide invaluable insights into how these objects handle the solar wind, how their tails behave, and what their chemical makeup reveals about other planetary systems. This serendipitous event also underscores the importance of flexibility in space mission planning. Hera and Europa Clipper were designed for entirely different objectives, yet with careful adjustments, they can seize this once-in-a-lifetime opportunity. It's a reminder that in space exploration, adaptability can transform routine missions into historic discoveries. Teams are working at breakneck speed to optimize instrument settings and observation schedules, knowing that the encounter window is both fleeting and precious. Future interstellar objects may present similar surprises, and the lessons learned from 3I/Atlas will help shape how missions respond to these unexpected guests. NASA's Comet Interceptor is already being designed with surprises in mind. It aims to rendezvous with a previously unvisited comet, potentially even an interstellar visitor, offering an unprecedented chance to study one of these alien travelers up close. Data from Europa Clipper and Hera will inform everything from instrument selection to timing strategies, ensuring future missions can maximize their scientific return. This is a perfect example of how one unplanned encounter can have a ripple effect, shaping decades of interstellar research. As 3I/Atlas hurtles through the inner solar system, its tail isn't just a static plume, it's a dynamic, electrified playground for solar wind interactions. Imagine the solar wind as a cosmic breeze, invisible but relentless, constantly buffeting the tail, pushing ions and dust grains in unpredictable directions. Some of these particles spiral along magnetic field lines, others collide and scatter, creating turbulence in the otherwise delicate structure. For Europa Clipper, every particle detected and every magnetic twist observed is like reading a diary from another star system, a record written long before our Sun even formed. Scientists are particularly eager to see whether 3I Atlas behaves like comets from our own backyard, or if it carries strange alien signatures that hint at environments utterly unlike our solar system. NTHE timing of the encounter is a matter of cosmic choreography. Hera's pass through the outer reaches of the tail from October 25th to November 1st will primarily serve as a positional check. Even without plasma detectors or magnetometers, Hera's trajectory data will provide scientists with a three-dimensional map of the tail's structure, confirming or correcting the tail catcher predictions. This is more than just a supporting role. Hera is essentially the cartographer, mapping the boundaries of the comet's extended influence. Without such positional verification, interpreting Europa Clipper's more detailed data would be far more challenging. Hera's contribution ensures that the team can contextualize every particle and field measurement, turning what could have been a vague encounter into a scientifically robust dataset. Europa Clipper, arriving from October 30th through November 6th, is where the real magic might happen. Equipped with magnetometers, plasma instruments, and charged particle detectors, it can sample the tail's environment with unprecedented detail. Scientists hope to capture variations in particle density, temperature, and velocity, and to observe how the comet's outgassing interacts with the surrounding solar wind. One particularly intriguing possibility is that the tail could generate localized magnetic perturbations, essentially small-scale space weather events. Detecting such phenomena would provide insights not just into 3I/Atlas itself, but into the behavior of interstellar objects more broadly, including how they transport material and interact with other stellar systems. In essence, Europa Clipper could turn a fleeting flyby into a full-blown interstellar laboratory experiment. NTHE scientific payoff is potentially enormous. Interstellar comets, like 3I/Atlas, are, in a very real sense, chemical emissaries from distant star systems. They carry within them frozen records of their birthplaces, ices, dust, and organic compounds that formed under conditions vastly different from those in our solar system. By measuring the composition and behavior of these materials, scientists can start to piece together the diversity of planetary formation across the galaxy. Do all star systems produce comets with similar chemistry, or are there wildly different recipes scattered among the stars? How do interstellar objects respond to a new solar wind environment compared to comets that have been shaped entirely by our Sun? Even a few hours of data could help answer these questions, providing the first in-situ confirmation of theories that have, until now, relied on remote observation and computer modeling, not on Venus-Bellard. One of the more subtle but equally valuable aspects of this encounter is the chance to test and refine predictive models. Tailcatcher and other comet tail models have been extensively validated within our own solar system, but interstellar comets offer a unique challenge. Their composition, density, and outgassing behavior may differ from what we've seen before, potentially revealing new physical processes at play. By comparing observed particle densities and magnetic field interactions with model predictions, scientists can improve their understanding of cometary physics in a more universal context. This means future missions will be better prepared to study other interstellar visitors, making each subsequent encounter more scientifically productive than the last NOF course. This unprecedented opportunity comes with plenty of challenges. Space is, after all, unforgiving. Particle densities in the tail's outer regions are extremely low, meaning that Europa Clipper's instruments might only capture a few sporadic readings during the flyby. Solar wind fluctuations can nudge the tail out of alignment, and tiny timing errors could result in missed data. Yet even these failures are valuable. Null results, moments where no measurable interaction occurs, still provide critical information about the limits of detection and the physical properties of the comet's environment. Scientists know that in space exploration, absence of evidence is not absence of science. Even silence tells a story, helping to constrain models and set expectations for future observations. Beyond the immediate scientific returns, this encounter highlights the elegance of flexibility in space mission design. Neither Hera nor Europa Clipper was built with interstellar comet observations in mind, yet both can contribute valuable data with only minor adjustments. Hera's trajectory verification and Europa Clipper's detailed measurements exemplify how spacecraft can pivot to seize unexpected opportunities. This adaptability is likely to become a cornerstone of future mission planning. As our ability to detect interstellar visitors improves, the solar system will be filled with transient opportunities, each presenting a narrow window for observation. Learning to respond quickly and effectively could unlock decades of previously inaccessible scientific insights. Looking ahead, ESA's Comet Interceptor mission is a direct response to this kind of unpredictability. Scheduled to meet a previously unvisited comet, Comet Interceptor is designed to handle whatever the universe throws at it, including, potentially, an interstellar visitor like 3I Summons. Data from Hera and Europa Clipper will inform the design and operation of Comet Interceptor, from instrument selection to observation strategies. In effect, this serendipitous encounter is not just a one-off event. It is training for the next generation of interstellar exploration. Every ion detected, every magnetic fluctuation measured, will help engineers and scientists prepare for encounters that might happen with little warning, ensuring that humanity can make the most of these cosmic surprises. NA's The Tale of 3I/Atlas continues to interact with the solar wind. Europa Clipper may also provide insights into how interstellar comets evolve as they pass through the inner solar system. Will the tail remain stable and elongated, or will it fragment and twist under the combined influence of solar radiation and the solar wind? Observing these processes in real time will allow scientists to compare interstellar comets with familiar solar system comets, highlighting similarities and differences that may reveal fundamental truths about how comets form and evolve in different stellar environments. The measurements could also inform models of how organic molecules and water are transported across the galaxy, with implications for our understanding of planetary system formation and even the distribution of the ingredients for life. NTHE, broader implications of this encounter extend beyond pure science. It's a testament to the ingenuity and preparedness of humanity's space programs that we can turn a chance alignment into a potentially groundbreaking experiment. It shows how even missions with very specific goals can adapt to unexpected opportunities, producing results that may redefine our understanding of the cosmos. The fact that two spacecraft, Hera and Europa Clipper, can play complementary roles in this event underscores the importance of coordinated, flexible mission planning. Hera maps the tail's structure, while Clipper dives into the details, capturing data that could reveal the comet's chemical composition, plasma environment, and magnetic interactions. Together, they form a multifaceted observational team capable of turning serendipity into science. Of course, the clock is ticking. The comet's passage is brief, and the encounter window is limited. Hera will complete its pass first, providing essential positional verification, followed closely by Europa Clipper's detailed measurements. Every hour counts, and mission teams are working tirelessly to ensure instruments are correctly calibrated and observation schedules are optimized. Any delay or misstep could mean missing the opportunity entirely. It's a high-stakes, high-reward situation, a short-lived, unplanned window that could yield the first-ever in-situ observations of an interstellar comet's tail, forever changing our understanding of objects from beyond our solar system. Once the data is collected, or even if it isn't, scientists will spend months or even years analyzing the results. Every particle counted, every magnetic fluctuation recorded, will be compared against predictions, models, and previous cometary observations. Even partial data will help refine theories about how interstellar comets interact with the solar wind and how their tails evolve. The encounter also serves as a real-world test of tailcatcher and other predictive models, providing a feedback loop that will improve accuracy for future interstellar comet observations. In short, this one serendipitous fly-through could generate decades of scientific insight, shaping the way we study objects that wander into our solar system from the far reaches of the galaxy. A time 3I/Atlas departs our neighborhood. The observations collected by Hera and Europa Clipper will mark a historical milestone. Europa Clipper may return the first direct in-situ measurements of an interstellar comet, while Hera provides the crucial context needed to interpret the data. Together, these spacecraft demonstrate that even missions designed for entirely different objectives can adapt and achieve groundbreaking results when the universe hands us an unexpected gift. The lessons learned will inform future mission design, observation strategies, and our broader understanding of how planetary systems, and the comets that populate them, form throughout the galaxy. And so, what began as a chance alignment, two spacecraft coincidentally passing through the tail of an interstellar visitor, has become an unprecedented scientific opportunity. Europa Clipper and Hera, working in tandem, may provide humanity with the first tangible measurements of a comet born around another star, offering insights into composition, plasma dynamics, magnetic interactions, and the broader physics of interstellar objects. Success or null result, the encounter will be a touchstone for future studies, a reminder that space exploration is as much about flexibility and curiosity as it is about meticulous planning. And in the end, the tale of 3I/Atlas and its unexpected spacecraft audience is a story of cosmic serendipity, human ingenuity, and the unending surprises the universe has in store. From the swirling, electrified tail of a comet to the instruments of distant spacecraft, every observation contributes to a broader understanding of the galaxy we inhabit. The data returned may help answer questions we didn't even know to ask, shape future missions, and provide a glimpse of the alien worlds that exist beyond the reach of our sun. And for a brief shining moment, Hera and Europa Clipper will have been in the right place at exactly the right time to witness a visitor from another star system, an encounter that reminds us just how wondrous and unpredictable our universe truly is.